Good morning. Here we are once again. It is the physics video lecture, the psci 168 video lecture 11. And what are we talking about today? We ended last time with the drop chord. So let's do a quick review of that. We're going to make huge progress today. By the time the hour is over, satellite orbits will be part of our skill set. So we have a bit to do before we get there. So the drop chord, which I recommended that everybody try and construct and figure out. The drop chord was a chord that fell on a sounding board, and it had some clips attached to it at a very special spacing, so that when the clips fell onto the board here, the sound board, the rhythm was even. So these things are spaced clearly in increasing distances, but the rhythm you hear is just 1, 2, 3, 4. And you could do it with 5 and 6 if you had a taller chord. The distances actually grow very rapidly. They grow quadratically. So that's what we had come up with. We did the drop chord. We find that the distance fallen is proportional to the time squared. So distance fallen, d, is proportional to the time squared. That's where we ended, okay? And so these distances go as 1, 4, 9, 16, 25, 36. If you had a drop chord with sufficiently, massive objects, you could stand on a building and drop down and extend these numbers quite a ways, okay? But they grow quadratically, so they grow quite rapidly. So here's what we have found because of that, right? This is a drop chord. What we're investigating is free fall. And we have just discovered the law of, or come further along in our characterization of free fall. And what that is the following. This d proportional to t squared implies that d divided by t squared is equal to a constant. But the units, distance over time squared, are the units meters per second squared, and that is an acceleration. So let's write that here. The units of d over t squared are meters per second squared. And this is an acceleration. So so let's write that down, acceleration. So what we found is the law of free fall is motion with constant acceleration. So free fall is motion with constant acceleration. We already knew it was accelerated because the speed is changing. But we know more now, motion with constant acceleration. Fall is motion with constant acceleration. Very important. From here we can take our kinematic definitions and do a little bit of algebra and actually get the exact laws of free fall. So how much of that do we want to do? Let's write them down. This derivation is not something you have to master, but I want to show it to you because I want you to get confidence in the idea that everything we're doing is a logical progression. And not only is it a logical progression, it's one that you can follow and think along with. And that'll give you confidence in all of the physics that we're learning, and that'll give you confidence in everything we learn about energy. So we're going to get the laws of free fall So we're going to call this next topic constant acceleration kinematics. Constant acceleration kinematics, okay? So I have the following definitions. I have V equals delta x over delta t. And let's write here average. V sub average is delta x over delta t. This translates to x minus x0 equals V average times t. Okay. And if we were to graph that, it would be a straight line graph. Then we have acceleration equals delta V divided by delta t. And this translates to, when I say it translates, I'm just cross multiplying and simplifying the formula. Okay. V equals V0 plus A times t. So I'm just replacing the delta t times t. And if I were to graph this one, here let's just number this little sequence of ideas. If I were to graph this thing here with a constant acceleration, this is a straight line graph like that. This is a straight line graph, V as a function of t. V as a function of t. It's just a straight line. And because of that, fourth point for acceleration equals constant, V average is equal to V0 plus V divided by 2. Okay. And now I take this equation in here and plug it into here. Now x minus x0 equals V average t, V0 plus V divided by 2 times t equals V0 divided by 2 times t plus V divided by 2 plus 1/2. And V is V0 plus AT times T equals V0 divided by 2 times T. Got to pick up the same thing again here. V0 T plus 1/2 AT squared. Okay, so those are the steps out of our definitions. And out of this particular thing here that I labeled with a star. And so what we finally get is, here, let's keep numbering this, we finally get the following. And I'll put them in a box right here. We get the kinematic formulas. Let's get the kinematic, we'll write it this way. X equals x0 v0 t plus 1/2 at squared, and v is equal to v0 plus a times t. So those contain everything we have to know about constant velocity constant acceleration kinematics in one dimension. And again, you don't have to memorize this at all. If you're interested in pursuing these steps carefully, you'll definitely learn something and pick up some skills. We're going to use these things to discuss freefall. Now, the acceleration A is a constant, and in the case of freefall, we give it another name. Okay? So continuing here, free fall. Acceleration is called G, and it has the value 9.8 meters per second squared. That's called the gravitational acceleration. Gravitational acceleration. Okay, so this G, 9.8 meters per second squared, and of course it's accelerating down. So if we're worried about, or thinking about the up and down directions, we can go like this. We can have the positive direction up. I can change the name to the y-axis. So for the case of gravity, I'm going to write y equals h minus 1/2 gt squared. So I translated this thing. I started at h. What I'm going to do is just drop something out of the air, drop something down. I start at h, and I'm not going to throw it with any speed, initial speed, so it's just going to drop. And this will be the formula for dropping an object. Okay. H minus 1/2 gt squared. If I wanted to throw it up in the air, I would keep this term here. But I'm trying to keep this simple enough. So the question is, how far does something fall? How far does something fall? Say you start at a height h. How far does it fall after 1 second, after 2 seconds, after 3 seconds? Now that we have this number, we can evaluate that. So I'm going to make a little table of values for you guys. That's the important quantity there. Let's call this distance fallen. Distance fallen when we release an object from rest. So I can just make the positive direction down now and just ask how far has it fallen. So distance fallen, d, is 1/2 gt squared. I'm not worried about the positive or negative direction, just how far does it fall. And it's, it's this term here, 1/2 at squared with the gravitational acceleration. So let's make a table here. Well, first let's do an example. Example, t equals 1 second, d equals 1/2 9.8 meters per second squared, 1 second the quantity squared. So the second squared and the second squared cancel, and we're left with meters. 9.8 divided by 2, 4.9 meters. Yeah, you don't think it's that far, but can't see the ceiling here, but let's go ahead. We have the top of the board. So here's the first meter. There's the second. There's the third. The top of the board is 3 meters high about. You need roughly 2 more, and that's how far something falls in 1 second, 1001, okay? And then how about after 2 seconds? So now we'll make our chart. For 2 seconds, we would just take 2 seconds and square the 2, okay? So then it's going 4 times as far, so it'd be 4 times 4.9. So D, so let's write T and D, T and D. So in seconds and in meters, and then 1, 2, 3, 4, we've got the 4.9 meters, and so 2 squared is going to be 4, so that's 19.6 meters. 3 and 4, 3 is going to be 9 times 4.9, and 4 is going to be 16 times 4.9, okay? So 4 times this. So go ahead and calculate these out. I'll just write homework here, but complete the table. You can even do 5 seconds as well. So that's how far things fall. The distances grow enormously. And the reason you don't see that is that if you drop, say, a tennis ball, it's going to stop speeding up as fast. If you drop a steel ball, a brick or something, it will traverse these distances pretty rapidly. Okay, so there's the distance fallen time squared formula. That's the one thing we needed. And there's a second formula I'm going to do a simple version of. We want to add a third one of these, namely by eliminating the time. So I have this, I'm gonna, let's see, I'll go ahead and send this over. So you'll notice we have velocities here, and it's possible to eliminate the time and have an expression that just talks about accelerations, distances, and speeds. So that's what I'm going to do. In fact, I'm going to do a simple version of this. So solve for time in v equals v0 plus a times t, that second equation. So t is equal to v minus v0 divided by a. It's a simple algebraic step, right? V minus v0 divided by a, and plug into here. Plug into x of t, which is this one, and here's what you get. You get v squared equals v0 squared plus 2a x minus x0. Leave room in your notes. If you want to do that algebra, it's a good exercise. I'll just write show this if you're so inclined. What I want to do is get the simple case of this for free fall. What we're going to do is let v0 equals 0, a be minus g for down. Actually, we'll just let a be equal to g, a be equal to g for free fall, and x minus x0 be equal to h. So h is a height that we're free falling, g is the free fall acceleration, and v is the speed. Here's what we get. We get v squared is equal to 2gh. So if you're in a physics class, we would actually work with these things and all, with the whole complication, but I just want the simple cases. Okay. So the simple case for free fall is this, and the simple case is also this right here. D and h are being used interchangeably. They're distance or a height. Okay. Good. So what this will tell you is if something falls a distance h, this is how fast it's going when it reaches the bottom. Okay. So this relates velocities, accelerations, and distances. Velocity, acceleration, and distance. Okay. So I haven't really left anything out. This is a somewhat rapid but reasonably thorough discussion of the kinematics. We have, in addition to these two formulas here, this one, you may want to make a chart with just these three formulas. And then we have my simplified versions that we're interested in using as well, okay? And there's, yeah, okay, good. Let's see how we're doing for time here. Okay. We want to get to the orbits, right? The orbits of satellites around Earth. And we had to have the free fall. So again, distance fallen in 1 second, 4.9 meters. Very useful and important fact. And then it keeps growing. 2 seconds, 19.6 meters, and so forth. So 4.9 meters in 1 second. It's accelerated. This formula we're going to use later, not right now, later when we get back to energy. Right now we're just doing motion. So this is a pretty thorough discussion. Good. So next I'm going to do a demonstration. Namely what I have here at the board, and we will add one more version of these formulas. So what do I have right here? This is a car that will move along a track, pretty low friction. So what I demonstrate with this right now is what's called uniform motion. This is constant velocity motion. And I just give it a push, and it's going just as fast now as it was when I let go of it. Okay, that's the idea, uniform motion. So let's write down here demonstration uniform motion, and we'll use these formulas once more. So demonstration uniform motion. And just so we have my track here, I've got a car, got a little tower on it, that's going to come into play as well. And it's moving here from left to right. Now what about uniform motion? There's a formula for it. We can take this x equals x0 plus v0t equals half acceleration t squared. And the thing is this, uniform motion means no acceleration. So uniform motion equals constant velocity, and that means acceleration equals 0. Okay. Important point. Remember we had acceleration equals delta v over delta t. Well, we can think of that as the change of velocity. If the velocity doesn't change, then it's 0, and then the acceleration is 0. Now, if we have this acceleration equals 0, you know, as opposed to speeding up and slowing down, right? This is just drifting across. It's neither speeding up nor slowing down. Then this is a 0 as well. And then we can translate this equation into a distance equals v0t. So the distance just grows uniformly with time. So this is uniform motion. Okay, call it right here uniform motion. This is the formula for uniform motion, meaning just constant velocity. Okay, so once again, there's the uniform motion. But now there's a little a little added feature here. Turn this switch on. So this thing actually has a little projectile launcher in it. It launches a ball straight up in the air. Boom. Okay, now what I want it to do is launch it perfectly straight so it catches it in the basket. Pretty good. Okay, this one's a little hard to control perfectly. If I monkey around with it, it'll just be worse. But give it a couple tries. So what we're demonstrating here is, that was actually pretty perfect. This is free fall. Okay, it's just throwing a ball up in the air and catching it. So it goes up, stops, comes back down. That's the free fall. And what I'm going to demonstrate now is, okay, once more. Free fall, catches it. So there's free fall, straight up and down, and uniform horizontal motion. Now wish me luck on this, okay? I'm gonna send it through here. It's gonna kick the ball in the air and we'll see what happens. Perfect, it catches it. See how that comes out on the video. I think we're getting enough frames per second. Shouldn't do this again, right? Because it just worked, but this should be reproducible. Yes, so how is it that the car can catch the ball independent of my doing? The answer is that this free fall motion and the horizontal motion are completely independent of each other. As long as there's no wind resistance, this is thrown up and down, but it's it has the forward motion of the car even when it leaves the car. Okay, so this is a really crucial experiment, and in a sense, it's really trivial. If you were driving in a car, okay, you're a passenger in a car going this way, and your driver's driving, and you throw something up in the air and catch it, you wouldn't even think twice about it. Okay, as long as the car is going uniform speed. The outside people who see that would actually be observing this arc, okay, as the car goes by. Okay, so many examples of this. What we're going to say here for our demo projectile cart is what we're going to call this, the projectile cart. The projectile cart demonstrates the independence of the horizontal and the vertical motion. So yeah, you want a nice picture in your notes of the projectile cart here, which kicks the ball up. I've got another color. It kicks the ball up vertically, but because the cart moves over, it just caught the ball down the road, so to speak. Okay, so that's called the projectile cart. Catches the ball, but what it's demonstrating is vertical and horizontal motions are independent. Demonstrates independence of horizontal and vertical motion. Which means if we wanted to do calculations of this, it would not be difficult at all. First we'd do one, then we'd do the other, and they would both work. Independence of horizontal and vertical motion. And the reason that is functioning is because there's no friction or negligible friction. A lot of friction, all bets are off. Okay, horizontal and vertical motion. Important point. Okay, now let me see if I have time to talk about satellites. Yes, I do. This is going to be perfect. So what does this have to do with satellite orbits? Everything. We have all the ingredients in place to figure out how fast does a satellite have to go to successfully orbit Earth. Okay, yeah, we're pretty complete. Projectile cart, you can write down more if you want to, about it. Good. So now we're going to talk about satellite orbits. Using only things that we've learned and demonstrated in this class. Okay, we will call this satellites. There used to be a really good program called JTRAC, and it was from NASA that demonstrated that you could actually observe the satellite orbit tracks. It's been taken offline, but you could find JTRAC images. If you look up JTRAC NASA and images, you may find something. They took it offline. I used to show it to my classes, to a lot of different classes. But this will be a source of certain images that of what we're talking about right here. Good, so what about satellites orbiting the Earth? How does that work? Why don't they fall down? How high are they, and so forth? So what we're going to do is, first of all, talk about near Earth orbits. So what is near to Earth? We're going to draw a large circle. Okay, got us a large circle here. This is Earth. We know Earth's radius. We measured it, so to speak, in this class. We know Earth's radius, 6,400 kilometers roughly, okay? Big. So where is a near-Earth satellite orbit? I'll just draw it right here. There's our satellite. I'll just draw. Okay, there's a little satellite. It's orbiting the Earth. So how far is that? If this is 6,000 kilometers, that's already several hundred kilometers. So as long as the satellite is above the atmosphere, where it encounters no friction, it can move freely. And so near Earth could be even closer to Earth than my picture. And things like the International Space Station are actually up at these type of levels. They're not that far away. A couple hundred miles to San Diego, you go straight up, you're in outer space. Okay. That's one thing people aren't always aware of. So near Earth orbit, I could say H is much less than the radius of Earth. And H would be the height of the orbit above the surface of Earth. Okay. So that's the first thing. It must be above the atmosphere. To be away from friction, to experience no friction. And in that case, the satellite is in free fall. So you could just drop the satellite. Of course, it would come crashing to the ground. But it's free fall with a horizontal throw. It's the reason I demonstrated this thing for you. The horizontal speed and the free fall properties are completely independent of each other. So free fall, I'll say free fall with a horizontal throw. But what's a horizontal throw? Let's have an X and Y axis. You're standing here up at H, and you throw something horizontally like a baseball pitcher. throw it horizontally and it ends up landing on the ground. You throw it with more speed, it goes farther. Okay. But the vertical motion is completely independent. That's what we're talking about here, independence of horizontal and vertical motions. So the satellite is essentially something that's been launched and then given a horizontal velocity such that this arc that I'm drawing for the baseball, this arc just matches the curvature of Earth itself. And because of that, and because there's no friction up there, it never stops. It just keeps going around. So the satellite orbit is a horizontal throw with an adequate speed. That's all it is. And free fall is still in play. Just like with my cart here, the free fall law was still in play even though the cart was moving forward. So that's the whole thing. I may save the calculation for next time. Yes, I will. I'll wrap this up and make sure it's thoroughly done, and then we'll do the calculation next time. All over the horizontal throw. Your orbits have to be above the atmosphere because we have no friction. Remember, free fall was a fall with no friction, and the horizontal speed plays no role there. I'm going to consult the clock one more time because this calculation doesn't really take very long. Now that we have it set up, here's what I'll do. We'll set up the calculation a little more, and I will give the result of the calculation as a homework problem. You guys are going to love this. Okay. So we're going to turn this picture for a near-Earth orbit into a calculation. So now that we see the ingredients, we're going to take our large sphere here, or circle, and we're going to imagine, since it's a near-Earth orbit, we're going to imagine that we're actually just launching, from the surface, okay? It's a completely smooth ball, and we're launching horizontally like this, okay? And what we want is the speed that will do what the red arc is doing. It'll keep falling around the Earth. So here's the construction. We draw this fairly large. This is really one of my favorite constructions too. Okay, so I have a triangle, I have a right triangle, and apparently this is the radius of Earth, and here's the radius of Earth, and this little piece on the hypotenuse I'm going to call H. I'm going to call this here D. Well, we're going to call it L. And now we're going to do the Pythagorean theorem. But let's write down what these things mean. R equals radius of Earth equals 6.38 times 10 to the 6 meters. Okay, so we know that. We're going to let H equal 4.9 meters. The reason is that's the distance something free falls in 1 second, right? Free falls in 1 second. So what happens is we threw it horizontally, but it actually went along this arc here, and that distance H is for t equals 1 second. And what that means is L equals the distance forward, right? It's the horizontal distance in 1 second. And t equals 1 second. That's the free fall in 1 second. So it's going along the red arc, but you could say it went forward and it fell down. Kind of like this here, okay? So what we have is apparently a Pythagorean theorem. We have r squared plus l squared equals r plus h. The quantity squared solve for L. You can use a calculator if you want. So this is the homework. You do the homework, you give it a try, because I'm definitely going to do this for you guys as well, okay? What makes this easy is that h is very small, but you can use a calculator and figure out what L is. It's coming here as the L squared. When you expand this out, the r squareds cancel, it simplifies, and then you can use some numbers. Homework, solve for L. And what is L? It's that distance, so v orbit equals L over t, with t equals 1 second. So v orbit will be this many meters per second. Okay, you guys give that a try. We'll be back to work on it together. See you next time.